How long would you stay in Taiwan?
Only this week, I think, until Sunday, maybe.
Oh.
Yeah, Sunday.
Is it spring break in?
Yeah, we have a break. 2 weeks no class. 2 weeks no class. This week no class. This next week no class. But the official holiday is Friday and Monday, I think. And yeah, there's a massive move on the borders for people visiting the graves of the ancestors. Yeah. Yeah, I mean, Macau people, some of them, if they have ancestors in mainland China, then they cross the border to visit the.
Right.
Yeah. Some of them, not all of them, but some of them.
It's a big day or
Yeah. Hong Kong also, some of them, yeah, but some people might select to go before, 1 week before, 1 week after. It depends where I'm going.
Hello, everyone. Welcome to today's seminar. So our speaker today is Professor Ivan Arraut, working as assistant professor at the University of St. Joseph in Macau at the Institute of Data Engineering and Science. And he obtained his PhD from Osaka University. And then he held different positions, for example, at the Chinese Academy of Science in Beijing. Then he moved to the University of Science in Tokyo and to the Open University of Hong Kong before he then started his position in 2022. And he will talk today about Hawking radiation as a mechanism for spontaneous symmetry breaking. So let's welcome our speaker.
Yeah, thank you very much. Thanks for the introduction. Yeah, my name is Ivan Arraut. University of St. Joseph in Macau is the only Catholic university. In Macau has a Catholic tradition due to the Portuguese influence. Then, in the same way as Hong Kong has the Christian influence due to the British, etc. Before, where I was in CIS, there was some grants, fellowship for postdoc like CISP, AI, FI, and JSPS fellow in Tokyo. And I graduated from the University of Osaka. They changed the name. Now it's not Osaka University. Now it's called the University of Osaka. More or less the same name. But my supervisor was Yutaka Hosotani and Hideo Kodama. Kodama in KK because I spent 1 year, the last year of PhD. I finished publishing only with Kodama at the end. The last year of PhD was KK High Energy Accelerator. So it was a nice experience there. I come to talk about Hawking radiation as a mechanism of spontaneous symmetry breaking for no, it's not moving. Okay, I will directly. Why is not moving? Okay. Okay, now it works. Okay, of course, first, let's make a review about what is asymmetry. Asymmetry is any transformation leaving invariant system. If we rotate this ball, of course, the ball doesn't change the shape, right? This is a global symmetry transformation. It's different to gauge symmetry. Gauge symmetry, will be a gauge symmetry here, well, if I deform 1 point of the ball, it will change the shape. And for restoring the shape, I have to introduce a gauge field. So the gauge field, the role of the gauge field, for example, the photon in QED, is to restore the symmetry. This is just an example of dihedral group in group theory. So any transformation around this axis, flipping the triangle, leave the triangle invariant. And of course, under symmetries, the action doesn't change up to total derivative. So we know perfectly we apply any symmetry transformation to an action, and it doesn't change. So why are symmetries so important? Because they govern the interactions. If I change the symmetries of the interactions, they change their behavior. Gravity would not be gravity if I change the symmetries. I mean, at least the law of gravity as we perceive it, the traditional Newtonian law at the weak field approximation will be different. For example, if I change symmetries in the strong interaction or weak interaction and others, the interactions will behave completely different. Symmetries tell us which quantities are conserved, explain the behavior of symmetry, and when broken spontaneously, of course, the collective behavior emerges now. Collective behavior like in superconductivity, the BCS theory, or ferromagnetism, and of course, if we go to the gauge at the gauge level, of course, we have the Higgs mechanism and so on. So, what for connecting symmetries with black holes, first let's explain a little bit what is a black hole. A black hole is a compact object, very compact. So any object, if I can collapse it and compactify it at a radius smaller than its gravitational radius, well, this is a spherical symmetry. I am not considering rotations or these kind of things. But if I can take, for example, the Earth. You calculate 2 GM of Earth is like 3 or 4 millimeters, more or less. If I can put all the mass of the Earth inside those 3 or 4 millimeters, that's a black hole. Very, very small black hole, but it's a black hole. Of course, the black holes are not formed naturally like that. They are formed by collapse of stars, etc., when they die and so on. But of course, technically, we can make black holes if we can compactify any object. A spoon, if you take a spoon and a little spoon of a black hole will be very, very, very heavy, right? Because the density is huge. And of course, the gravity is so intense, classically, the light cannot escape, and nothing can escape, not even the light. So as you know, any object in our planet, we have escape velocity for sending a rocket to the space or any object. Remember the thought experiment of Newton that he imagined a bullet going out from a mountain, from a cannon going out, and he imagined that the bullet was thrown faster and faster, and if you throw it fast enough, it finishes in orbit. Well, that's the escape velocity. We have escape velocity here. In any planet, we have escape velocity. The larger the planet, the larger the escape velocity. In the black holes, there is no escape velocity. So you cannot escape, basically. Not even the light, classically. So as you remember, when Einstein did his theory of general relativity, he formulated the Einstein equations, which are nonlinear equations. At the particle physics level, of course, we understand that the nonlinearity comes from the interactions between gravitons, because, of course, in electromagnetism, the photons, they don't interact each other, at least if we don't consider these QED corrections. So classically, gravity is nonlinear, and the Einstein equations are nonlinear. So Einstein believed that his equations had no solutions by the time. I mean, he didn't know how to solve them. So Schwager was the guy who found the first solutions under some assumptions. Of course, spherical symmetry simplifies everything. Some equations which become a mess. At the end, it finished being only one-dimensional equation. If you remember the geodesic equation, at the end, it becomes an energy equation, the kinetic energy plus potential energy, and you can derive everything. Everything depends on the radius at the end. So, but in this Schwager black hole, of course, we have an even horizon. We have this Schwager radius measured like this. We call this even horizon, but more generically, this is called gravitational radius, because even our planet, any object has, you can calculate 2 GM for any object, no? So, well, it's called even horizon only in the case when you can compactify the mass of the objects inside this radius, then that's a black hole. And of course, this Schwager metric, this is the Schwager metric in matrix form, is diagonal. And of course, one of the things is, of course, this is the This is bashed, and this is the metric is explicitly written in the standard way, and again, the event horizon. And of course, the time, we cannot deny the success of general relativity. General relativity has been so successful. It predicted gravitational waves, it predicted the dynamic of the universe, it predicted the gravitational time dilation, which is a phenomenon parallel to the time dilation which you see in special relativity. Remember, for example, that the GPS we use, make corrections of time. For the absence of gravity, the satellites have less gravity than our planet, and also they move too fast for keeping the orbit. So we have to make corrections in time for that. So it's applied to the technology. So it's true. So it's not fiction. Then these things are true. So we have to believe this part. And of course, when we talk about symmetries in black hole, the symmetries we are concerned are the symmetries which are related to the information which the black hole stores. Remember that the entropy of a black hole is proportional to the area of the horizon. Well, the entropy is proportional, and the entropy measures the information stored by the black hole. So technically, all the information of the black hole is condensed. I can project on the surface. So when people talk about holography, this is the oldest version of holography at all. This is the projection of the information of the black hole over the horizon. And of course, any change I make internally of the black hole, which keeps the same macroscopic properties, mass, charge, and angular momentum, I consider that asymmetry. And it's related to the amount of information which is stored. So black holes, this is the no-hair theory, are characterized by mass, charge, and angular momentum. So no matter what changes I do inside, as long as I keep the mass, charge, and angular momentum, I consider that asymmetry. And this is related to the amount of information stored inside, which we cannot see because it's behind the event horizon. And of course, it's proportional to the area of the event horizon. So now let's jump a little bit for understanding what is spontaneous symmetry breaking, and then we will see how to connect that and why Hawking radiation emerges as a mechanism of spontaneous symmetry breaking. Spontaneous symmetry breaking is a phenomenon from condensed matter physics, actually. It was taken by condensed matter. From condensed matter, Yoichiro Nambu realized that he could apply this mechanism in particle physics. Yeah. Well, of course, in condensed matter, there are some differences. In condensed matter, sometimes the Nambu-Goldstone bosons have a dispersion relation which is quadratic. That doesn't happen in the high energy level. And also the counting. The counting is an issue. Sometimes two broken symmetries in condensed matter corresponds only to one Nambu-Goldstone boson. In high energy physics is 1-1, the relation. Each broken symmetry is related to one Nambu-Goldstone boson. So spontaneous symmetry breaking is like we have a potential. Technically, this potential was normal, was like this, like harmonic oscillator. And you are sitting here comfortable, like just you are here now, very comfortable. And then suddenly something happens. You change the parameters of the system. The equivalent is there is an earthquake here. The parameters of our system change. And then we are trying to find a new equilibrium condition. Because we are in an unstable equilibrium. The equilibrium condition could be you falling on the floor or we falling on the floor, with myself, etc. In the case of a system, any external perturbation may force the system to select one vacuum. The direction, it depends on the direction of the perturbation. So the perturbation, if the perturbation points in this direction, bam. If it points in the other direction, bam. And of course, there is an analogy, which is when you apply force over a bar, high enough, increase the parameter, of course, is the force. If you apply high enough, suddenly any perturbation will force the bar to deflect in any direction. So, of course, when the symmetry is spontaneously broken, there are associated some broken generators. And of course, some gapless particles emerge. This was the research done by Nambu John Alassino, Goldstone, Salang and Weinberg, they using the electroweak theory. Remember, the electroweak theory basically explore is the perfect version of the Higgs mechanism, which requires initially a spontaneous symmetry breaking, no, or gauge symmetries. They gauge it SU2 left, U1, etc., and obtain and apply the Higgs mechanism for obtaining the mass of the boson C and W, and the mass of the fermions also via Higgs mechanism. But for the case of fermions, they put the terms by hand. Actually, there is no fundamental principle explaining the origin of the mass of. Well, it's the Higgs, but for the fermions, they have to put the terms by hand. In the case of the boson C and W, it's natural because it comes from the gauge principle. So I will not explain that part here, but it's good to comment. So this is an example of a spontaneous symmetry breaking ferromagnetism. I have a ferromagnet, high temperature, all the domains pointing randomly everywhere. The magnetization of this object is 0. That's my order parameter. Magnetization 0 before the symmetry is broken. So I start to decrease the temperature. Temperature is the parameter I can control. I start to decrease it, and there is a critical temperature below which any small perturbation, the perturbation here will be the external magnetic field, forces all the magnets to align in one direction. So the magnetization here is different from 0, pointing vertically. Now, if the magnetic field points in a different direction, of course, the magnets will align in that direction. So at the end of the day, selecting this direction is equivalent to selecting one of these vacuums here. If I select another vacuum, it's equivalent to select another vacuum here. At the end of the day, if I assume all the possibilities, all the possible vacuums I obtain a trivial solution, which is, it gives me 0 again. So I recover the original vacuum again.
What does it mean by this, right-hand side of this figure? We have
This?
magnetic field, and all around, what does it mean by spontaneous symmetry?
Okay, well, first here, the rotation, if you rotate this system, you don't distinguish anything. In this case, of course, since all the magnets select one direction, the rotational symmetry here is spontaneously broken. I must remark that the symmetry is still satisfied by the Hamiltonian and Lagrangian. It's called spontaneous because the Lagrangian and Hamiltonian still satisfy the symmetry. It's the vacuum, the ground state, the one which violates the symmetry. It's not the Lagrangian or Hamiltonian. It's different to the explicit symmetry breaking, which is completely different. I don't know if that response.
No, I mean spontaneous symmetry breaking. You have domain wall. In this example, you have domain, wall, due to the spontaneous symmetry breaking, and each region is disconnected from another region.
Yeah, initially it's disconnected.
Yeah. When you apply magnetic field and they lie, what does it mean? What's the implication?
Well, here,
with respect to this spontaneous symmetry.
Well, let's assume that I apply this magnetic field here in this case, and the body temperature is too high. In that case, still the magnets will point randomly everywhere because the magnetic field will not be able to align them if the temperature is too high. But now I will reduce this magnetic field very small, almost zero. And I will point in this direction, and I will decrease the temperature of the system, which is the parameter I can control. And the temperature reaches some critical point below which any small magnetic field will force all these magnets to align. So in that case, of course, it's a collective phenomenon, collective behavior, and we have a spontaneous symmetry breaking. Other theories which use a spontaneous symmetry breaking is the BCS theory of superconductivity, when they pair the two electrons forming a boson effectively, and others, of course. And we use that in particle physics, but in particle physics, in the electroweak theory, it comes out, it finishes being the Higgs mechanism when you gauge the theory, because here we are considering only global symmetries in this case. So this is just the same. This is an example of Hamiltonian. Of course, the symmetry of the Hamiltonian is still invariant. I mean, the Hamiltonian is still invariant on the rotations, but if the magnets align in one direction, obviously I rotate the system around here, and the rotational symmetry here is lost for the vacuum state. So spontaneous symmetry breaking more properly, more general is you have a Lagrangian, the Lagrangian has kinetics and potential terms. So I am concerned about the vacuum condition. Vacuum condition is derivative of the potential with respect to the field equal to 0. It's like the Euler Lagrange equations, but ignoring the kinetic terms. In that case, of course, if you obtain the trivial solution, it's just the standard vacuum state. But under some combinations of parameters, the solution is not trivial. And normally in those scenarios, the symmetry is spontaneously broken. Now, more generally, in a standard case, when we have a symmetry, we represent it with a unitary operator. These are the generators of the symmetry. This is a parameter. Normally, the generators of symmetries, they annihilate the vacuum, the growing state. Because, of course, this U applied to the growing state will not change the growing state, right? Now, imagine that the symmetry is spontaneously broken. Obviously, the vacuum state, the generators, they don't annihilate the growing state anymore. They don't annihilate. Actually, the effect, if we apply this unitary transformation to this growing state, we obtain a different vacuum state. It's like rotating. It's like if I go to this potential, it will be like jumping from one vacuum to the other. So the effect of that unitary operation is to move from one vacuum to the other. Yeah, that's the effect. And of course, that's the direction where the Nabu-Goldstone bosons move. Yeah, they move in that direction precisely. So situations like this, of course, happen frequently in physics. We have plenty of examples. And if we go to the group theory perspective, normally we have a group under which the ground state is not invariant anymore, but there is a subgroup under which the ground state is still invariant. And the dimension of the Coset space, of course, tells us the number of broken generators, which normally is equivalent to the number of Nabu-Goldstone bosons. This is in standard situations, in condensed matter systems, specifically in those where the Lorentz symmetry is violated explicitly. This rule is not respected because two broken symmetries represent one Nabu-Goldstone boson, and the dispersion relation is quadratic and nonlinear. Myself, I studied that case by using some formulation before. This is a way to represent the order parameter. If you apply the vacuum expectation of the order parameter, in this case, the magnetization, remember the magnetization in the case of the ferromagnetism is different from 0. By using all the possibilities, all the possible outputs of order parameters is trivial. It's like assuming this vacuum plus this, plus this, plus this, plus this. There is always a diametrically opposite value. So that's why they will cancel at the end. If you sum all of them, it will give you 0. And that was the key point for something which I will show you later. Something I must remark is that each vacuum is a different Hilbert space, and they are orthogonal in the thermodynamic limit. So if I multiply this ground state with this, the product gives me 0 in the thermodynamic limit. That's demonstrated in several textbooks and so on. So let's go a little bit deeper. Normally, this is a standard case where we obtain a vacuum condition, remember, by obtaining the minimal of the potential. And normally the direction of that vacuum condition is arbitrary. And of course, we can always shift the vacuum and see which fields are massive and massless, etc. But a better way to see it is expanding the potential. For example, I have the potential, and I expand 0 order. The first order is 0 because since we are around the minimum, we are expanding the potential around the minimum value. The derivative of the potential with respect to the field will be 0, but the second derivative not. So the second derivative will give me the mass term. This is a mass matrix, and this term is important, of course. This I mentioned already, but with this term, I can develop the Nabu-Goldstone theorem somehow. I can see if at least I can see when the symmetry is broken, some gapless particles will emerge. And this is done in this way. For example, this is the unitary operator, the expansion. This is the transformations applied over the ground states. And of course, this has to be 0 on the symmetry transformation. Obviously, if this vanishes, this is trivial. But if this is different from 0, then the mass terms will be 0. So these represent gapless particles emerging, and those are the Nambu-Goldstone bosons. Now, more generically, we have conserved currents, of course. As you know, we can define currents in I think the pointer doesn't work anymore. Okay, here. We can define currents in this way, and the 0 component of the current is the charge. So when we have the generators, broken generators, we usually will express in this form the integration over the volume of the 0 component of the current. Yeah? So it's important for me to keep the algebra structure. This is the standard definition of vacuum. For summarizing a little bit, it means that this unitary operator in the ordinary vacuum will not change the vacuum, but when the symmetry is spontaneously broken, this is what happened. The broken generator, which is this guy, because it generates the transformation, doesn't annihilate the vacuum anymore. So this unitary transformation, when applied to this ground state, will give me a different ground state. Now, the order parameter in general can be represented as a commutator between the broken generator and the Nambu-Goldstone field. This is a standard decomposition, which I think should be here. Yeah. Normally, they made this decomposition, taking phi2 as the Nambu-Goldstone field, phi1 as the order parameter. So obviously, the vacuum expectation value, when we consider single vacuum of the order parameter, this is the standard case with quadratic and quartic term, which we see in the textbook. One way to prove the Nambu-Goldstone theorem is expanding the previous commutator you saw here, this commutator. Here, I express this charge as the integration of the volume of the 0 component of the current, and it comes out to be this term here, this term. Equal time commutation relations, different from 0 because I am evaluating for a single vacuum. These are a complete set of intermediate states which I can introduce. These are identities. And of course, you can notice that there is a y and there is a y here. So, and they disappear here because they come from this, they go to the exponentials. We assume a space-time transactional invariance, and then you have to write this as this term with the exponentials of minus ipy and a exponential ipy here. And you have to operate over the kets. When you operate here, of course, it's trivial, but when you operate over the ends, give you these numbers here. At the end, of course, you have to integrate over the volume, and integrations over the exponential part of the momentum give you this delta Dirac. This delta Dirac is just telling you that the momentum goes to 0, and we know that. So this is precisely what happened in the infrared limit. But for proving that the mass, that the particles are gapless, because this represents the Nambu-Goldstone bosons, you have to prove the time independence of this expression. And this is proved in textbooks. You can find textbooks. If you calculate the derivative with respect to time of this commutator, in the large volume limit, of course, this term vanishes. So it's a way to prove the time independence. And if this term is time independent, then of course this has to vanish. So the only way to vanish is having gapless particles, which is Nambu-Goldstone bosons. Nice. I will mention a little bit something about Nambu-Goldstone theorem is that one problem was dispersion relation. Of course, it's linear when in the standard version of the Nambu-Goldstone theorem, because they are gapless particles, they are supposed to be gapless. A massless particle has linear dispersion relation. But in the case of condensed matter systems, as I mentioned, sometimes the dispersion is quadratic, and it's not difficult to see it because in condensed matter systems, when the Lorentz symmetry is violated explicitly, we have normally second derivative in space and first derivative in time. So it's obvious that the dispersion relation will not be linear, will be quadratic. But there are different ways to analyze this problem. before some time ago, I did some formulation. I put the other parameter. I extended to be a tensor in this way, and then I analyzed. I could connect this expression, which is this is the other parameter expressed as the commutator of the Brocken generator and Namu-Goldstone field. And of course, the same trick as before, you do the expansion and so on. But here the key point is that I involve a double commutator here. The idea was to analyze what happens when you have two sets of Namu-Goldstone bosons interacting with each other. If they represent the same degree of freedom, the dispersion relation came out to be linear. And if that represents different degrees of freedom, the dispersion relation, the same degree of freedom, the dispersion relation is quadratic. If they are different, the dispersion relation is linear. And the way to do that, of course, is a long process because you have to expand this double commutator. As soon as space-time translational invariance, you obtain these terms. And there was some notations to do. I will not go so deep in this, but these are quantum Yang-Bastel equations. And at the end, of course, I could prove that the Namu-Goldstone theorem emerges fundamental from this triangle. Each triangle here is each term here you see here in this commutator. 1, 2, 3, 4. And of course, by Yang-Bastel, whoever has studied quantum Yang-Bastel equations from the way how Witten and Costello analyzed in 2016, you know that the inequalities appear, but these are unequal. So the idea is when the four triangles are the same, N and N prime, they represent the same degree of freedom, and the dispersion relation comes out naturally to be quadratic. How do I do that? Well, grouping all the faces you saw on the right-hand side, and at the end, when you group the faces, it comes out that the cosine, the momentum expands at the lower order, quadratic, and the energy, or in this case, mass, expands at the lower order, linearly. This is some word I wanted to mention because it can be used, it can be applied in the case of black holes.
We start with a very simple example of Mexican head.
Yeah.
Yeah.
Well, in this case,
is that simple example to derive all this one?
Yeah, because in the Mexican head, what we are doing is this. What we are doing in this case is exactly here. What we are doing, that triangular formulation.
Okay, there's a Mexican head. I can use a scalar field to write down the Lagrangian.
Yeah, correct.
And there's a U1 global symmetry.
That's an example. That's one.
That's
the simplest one. Yeah,
I can
exactly. So when
there's a two radial mole is when after symmetry breaking, the radial mole is the Namu-Goldstone boson. Yeah, and then what happened to what you're going to say?
No, this part is another way to formulate the Namu-Goldstone theorem, these triangles here. What happened is that precisely if I go back to the what I am doing is this, for not confusing so much because I want to jump to the black hole part after. So it will be, it's like, what I am doing is instead of considering only one order parameter, I consider all the possibilities that you can have when you break the symmetry spontaneously. So all the possible other parameters. When I do that and I apply this expression, this can be expressed as the commutator because I don't have a board here, so I cannot express what. This can be expressed as a commutator of broken charge, Namu-Goldstone curve, this other parameter. And the broken charge, if there is Lie algebra, is another commutator of two charges. No? So when I expand this double commutator, I obtain four expressions, four terms. And those four terms turn out to be these four triangles, 1, 2, 3, 4, without going to details. And these lines represent Namu-Goldstone bosons, and this is the degenerate vacuum. it's a fictitious particle with zero momentum, zero energy. So there is a geometric way to represent the Nambu-Goldstone theorem.
The vacuum dV, what's dV?
The generic vacuum. dV is the SV. Yeah, because I assume, because sometimes when I am assuming the vacuum, I put dV for distinguishing from the single vacuum. Because when the symmetry is spontaneously broken, you go to only one vacuum. But if you are assuming all the possible vacuums, then I use the expression dV for not confusing it. It's like, I don't know if I use SV, for example. SV here, I am not assuming here. There is no sum on zero. And this is different from zero because you are in one single vacuum. But if you assume all the vacuums, this is equal to zero here. It's trivial. And each one
SV means
single vacuum.
A single vacuum.
Yeah, single vacuum.
In particular direction.
Exactly. In that particular. It is assuming all of them. Exactly. And these four terms are these four triangles. Yeah. So the point is that I will not go so deeply because I think not everybody has studied quantum Yang-Baxter equations, and it's not necessary to study for understanding Nambu-Goldstone theorem actually. But the summary is that from those four terms, there are only two independent because you can factorize these triangles. When n is equal to n prime, this happens in condensed matter systems, violating Lorentz symmetry explicitly. The dispersion relation comes out to be quadratic naturally, and this emerges naturally from this formulation. And this solves automatically the problem of counting because this is related to one broken symmetry. This is related to another broken symmetry. If they are the same, of course, the two broken symmetries are related to one degree of freedom, which is what happened in Lorentz violating when Lorentz symmetry is violated explicitly. Now, when they are different, you cannot factorize. When they are the same, you can factorize all the triangles. This is an issue. Okay, I will skip this part a little bit but there are some publications about this. If somebody's interested about this triangular formulation, because the idea is the quantum Yang-Baxter equations, the Nambu-Goldstone theorem emerges naturally from constraints coming from these quantum Yang-Baxter equations, which are mathematical expressions well established already in the past and studied by many people, including Witten, Jimbo, among others. And this is the way to express that. I will jump a little bit this part for jumping to what we care, the Hawking radiation. Yeah. Well, this at the end, of course, you have to analyze the infrared limit, which is what we care now. Now, Hawking radiation. Let's go to Hawking to understand why I think that Hawking radiation is a mechanism of spontaneous symmetry breaking. Already we mentioned that the black hole.
Before you go to the ask you some.
Sure.
Okay, in cosmology, if you have U1 symmetry, and then spontaneous Brooklyn, then you have domain, and the rotational symmetry with axon, only one single axon. Now you're telling us that may be more complicated than this picture.
Not exactly. What happens is
because each domain have its own vacuum in a particular direction, and the general vacuum, we can. And then it seems the interaction is much richer than what I thought.
Well, it's a way to interpret it, but I mean the simplest way is for the only way to implement quantum Yang-Baxter in that case is to sum all the vacuums, and of course each vacuum represents one direction where the symmetry could have been broken. Let's say when I take the pencil, the example of the bar, and I put the force, it can deflect any direction depending on some perturbations. Maybe somebody do, and it deflects in the direction, but somebody could have doing it. So I mean, it's when you don't know the direction, normally you assume all the possibilities, and then you obtain that trivial result, which allows you to implement the quantum Yang-Baxter equations in that case. And of course, that notation probably seems to be complicated, but it facilitates at the moment of analyzing, for example, color superconductivity, which is a phenomenon in nuclear physics, when we will go to QCD and so on, could be analyzed with this notation. Also in gravity, maybe it can be applied. Also, still there are scenarios where this formulation could become powerful, but it's simply another formulation of the same thing. The difference is that since you don't know which direction the symmetry will be broken, then you just assume all the possible vacuum, the possible outputs, and then you recover. It's a way to recover the original vacuum, actually. One way to recover the original vacuum is you assume all the possible final vacuums, and then you recover the trivial vacuum again. And that's a key ingredient in Hawking radiation also. I mentioned that because in Hawking radiation that applies. But for understanding why, it's okay. Okay. Okay, later. Hawking, what he did is a semi-classical. I mean, we don't have quantum theory of gravity. Of course, we have candidates of quantum gravity. We have a string theory, a serious candidate, nice, because, well, Schwarz many years ago realized that there was a spin-2 field floating there. It was a theory created with a different purpose, actually, but and it was kicked out from the science, actually, from physics. Nobody was using, but Schwarz and other guys, they noticed there was a spin-2 floating, and they said, this could be a theory of quantum gravity, and then it resurrects string theory. We have other approaches, whichever it is, we don't care at this point. What we care is that Hawking instead, he didn't use any quantum theory of gravity. What he did is to take a classical background, the spatial, well, initial spatial, of course, maybe with some charge, it will be René-Osron, whatever. But the point is that he used a classical background, and he put a quantum field moving around that background. Quantum field. That's why there are textbooks. You will find textbooks of quantum field theory in curved spacetimes. Actually, there is one very good book about that, or many good books about that. But in summary, is that Hawking realized that the quantum field, if you expand the quantum field before the formation of the black hole, it's a simple expansion like this. Well, the positive and negative frequencies, as usual. Remember, in Minkowski space-time, these frequencies never mix. In curved space-time, they mix, and that's what gives ring out Hawking radiation. After the formation of the black hole, you have the same field, the same quantum field, expanded in this form. Now you have two sets of modes. One of them people ignore completely because they just go inside the black hole, and the others is the one which you compare. So these two modes, actually, in this case, will be this and this A dagger, the A's and B's. I compare. And the way how he did was by using Bogolubov transformation in this way. And actually, this is not, well, this notation, I shouldn't have shown this because this corresponds to another research, which is quantum depletion. Because in condensed matter systems, actually, it's not difficult to know why Hawking had this idea. Because in condensed matter systems, these things happen. When you put a condensate at a temperature very, very, very low, where nothing is supposed to evaporate, still some particles escape via quantum mechanics. It's a quantum mechanism. Then, and the way to analyze is exactly the same as Hawking did in the paper of black hole evaporation. So I think Hawking already knew, probably. He would not say that, of course. But probably Hawking knew that in other fields this phenomenon happened, and then of course he mapped this to. It's similar to Nambu. That's why exploring different areas is important, because what Nambu did is to take for the Nambu-Goldstone theory. No, he took the condensed matter, because he was condensed matter physicist at the end. He took those ideas and he portrayed them in particle physics, high energy. And that's how the Nambu-Goldstone theory can apply, and those kind of things. He was one of the pioneers. I was lucky enough to meet him when he was alive, because he spent his last days in visiting sometimes the laboratory where I was by chance in Osaka, actually. Then, of course, you compare two vacuums. But this is where the things start to be suspicious. You compare to vacuums, vacuum. That's the key word, vacuum. Before the formation of the black hole, after the formation of the black hole. The spectrum comes out to be thermal. This brings out the information paradox because thermal spectrum doesn't have information, etc. Nice. And this is a clear, well, it's more or less the same. I think I repeated the slides probably. It's the same picture. But before the formation of the black hole, we can define a vacuum state, annihilating. After the formation, I can also define a vacuum local with this A applied, but it's different to this vacuum. So I can define two vacuums locally different. But when I compare them, this is the problem. When I compare is where the problem emerges, and is when one observer perceives particles with respect to the other. Is similar, not exactly the same as with the time dilation. In time dilation, remember, in special relativity, what happened? Every observer in their local frame of reference, they perceive the same time, normal time. I don't see any. It's when I compare with you that you are moving fast that I see, oh, my clock move different to you. Also with gravity, when there is the time in Mars and the time in the air is different. Not so different, but if you accumulate throughout the centuries, it will be very different. So the same happens here. You can define one vacuum locally. I can define also, I can put a different vacuum equals 0. But when I compare the vacuum of this guy with this guy, is different. And they are different when this coefficient, which mixes this guy is the guilty. Normally, they portray as beta. In the textbooks, it appears as beta, normally, in the notation of particle physicists and in gravity people, is beta. And that's why people say you're mixing positive and negative frequencies in curved space-time. So in this case, of course, if I apply this to this ground state, this guy will create a particle here. Then, of course, one observer will perceive particles with respect to the other vacuum. Then this is what brings out the black hole evaporation at the end. It's a comparison of vacuums.
What's the C and C difference? C and C.
These are modes which normally people don't consider them because they go inside the event horizon. So you cannot see them at the end. And the guys, the most which scale are these guys. So because you have a pair of particles, no? And that's what I was about to say is that it's a quantum effect. The vacuum has energy. The vacuum is permanently creating particle, antiparticle, electron, positron, and annihilate. Proton, antiproton, annihilate. And it is doing that permanently, frequently. The heavier the particles created, the less they live. They live less, of course. And the smaller the mass of the particles created, they live a little bit longer, but they disappear anyway. Of course, we cannot perceive that, but it has been measured. We have the Casimir effect. The Casimir effect is the perfect evidence that the vacuum energy is a reality. It's not fiction. So quantum field theory predicts that the vacuum has energy, and the way Hawking portrayed this phenomenon is the pairs of particles, they are created and destroyed permanently, and when they approach to the event horizon, when this happens near the event horizon, one particle accidentally moves inside the event horizon by conservation of momentum, the other has to move away, of course. That's how the Hawking radiation emerges. Well, of course, Hawking discovered a problem here is that since the spectrum he predicted is thermal and brings no information, the question is what happened with information? The black hole is supposed to have information, and then what happens? Do we have to wait? Should we wait until it evaporates completely for extracting information, maybe in the last bit, or there is something missed? So there are many proposals in the literature of the information paradox. Many people claim many different things. So it's difficult to know who is right or who is wrong or who is right. So it's very difficult because many people portray many different scenarios, including this Maldacena and Susskind, yes, the EP something that they made some duality, etc. These kind of things. But I will not go to this scenario. I will go to the simpler one. This is a way to portray Hawking radiation. And the vacuum is the guilty of this, the quantum vacuum. So, as I say, radiation is thermal. No information is violation of unitarity. Unitarity is a sacred principle of quantum mechanics. The information cannot disappear. You can claim, no, it disappeared. Well, in an isolated system, no, without external interaction, the information should be preserved. And we call that unitarity in quantum mechanics. And it's important to mention that since we mentioned vacuum energy, of course, the vacuum energy comes from the uncertainty principle itself, energy time uncertainty principle, and it comes from the ground state of the quantum harmonic oscillator, which is the algebra we use for quantizing a scalar field in quantum field theory. No? Remember, quantum field theory is the unification of quantum mechanics and special relativity. It becomes quantum field theory. We cannot do this mix with single particle approach because that was the mistake of Klein-Gordon initially, which bring out the unstable theory, no? The catastrophically unstable theory. Dirac rescued a little bit the theory because he realized that the problem was in the second derivative in space and time. He made first derivative in space, first derivative in time, and he could predict the positrons. Actually, he predicted, although his interpretation was wrong initially, he predicted. But at the end, even Dirac was wrong because that's a quantum field. I mean, the Dirac equation is a quantum field equation, and the Klein-Gordon equation is correct, but interpreted as a quantum field. We cannot interpret it as a single particle equation, but as quantum fields, multi-particle approaches. So, for summarizing is, of course, the vacuum energy is a reality. It's not an invention, it's not fiction. And this is a little bit more of the same, the quantum harmonic, I remember, the vacuum energy, which some people claim, if those guys who like cosmology, some people claim that the accelerated expansion of the universe comes from the vacuum energy when you integrate all these frequency modes, but of course, this gives you infinity. And if you put a cutoff, it's 120 orders of magnitude larger than the observations, but that's beyond the scope of this talk. And this is the proof of vacuum energy, the Casimir effect. If you put two parallel plates in vacuum, they attract each other. So the only way how they can attract or feel some force is that there is a vacuum doing something. Nice. So the vacuum energy allows the black hole to operate, was the interpretation of Hawking. So why is so important for me? Because what I want to see, and I still have time, right? Well, a little bit. What I want to see is what I care is the comparison of vacuums. And I want to create an order parameter of this process. Remember, the order parameter in magnetization in ferromagnetism was the magnetization. 0 before the symmetry is spontaneously broken, non-zero after. Well, here, before the formation, there are no particles, so particle number operator is 0. After the formation of the black hole, there are particles. This guy perceived particles when he compared the vacuum with the other. Particle number operator different from 0. That's my order parameter, the particle number operator. Particle number operator is my order parameter. But then, this is what I was mentioning before. There's an analog process in condensed matter. I don't know if this.
Send the picture, I guess. What do you mean by varying vacuum before the formation of black hole to the square black hole?
Because what Hawking did let me go here to.
Do you say the black hole
is
out of vacuum?
No. What I mean is that Hawking, in order to derive the effect, he put the quantum field. He expanded. Of course, this has to expand around some vacuum. No? So you have to define a vacuum for defining a quantum field. A vacuum where this operator annihilates that vacuum. Yeah. So this defines a vacuum before the formation of the black hole, and this defines these modes here. Outside the black hole defines a different vacuum. So when you compare these two vacuums is when you have the effect of Hawking radiation. And then I explode that physics for saying, of course, then this can be seen as a mechanism of spontaneous symmetry breaking if I take the particle number operator as the order parameter. 0 here, and non-zero here. And then I can construct. Yeah.
I have also a question on this part. Okay. So now, okay, before the black hole is formed, you can define the operator B, right? And then after formation, then you define the operator A. What's the guideline to tell how to get the A from B?
Okay, that's Bogolubov transformations. They have to be, I mean, for it's precisely the transformations. You have to apply the Bogolubov transformations for connecting the two modes. And then, of course, if you let's apply the vacuum expectation value of the particle number operator, which is adaga A, no? Adaga A. Adaga A vacuum expectation value, well, I use this vacuum instead of the vacuum defined by this guy. I can define a vacuum here and it will be trivial, but that vacuum is different to the vacuum before the formation. Then I want to compare with this vacuum. Then I meet the vacuum expectation value here, A daga A, and I obtain this. At the end, this vanishes because this annihilate, but this doesn't vanishes. And at the end, we really normal this square.
The purpose for this transformation that you want to create the number of the particle number, right? So why can you do this? This is a putting by hand, or you know the phenomenon. So then okay, to understand this phenomenon that we define this operator A. Can we understand it in this way?
Well, some by hand, not exactly by hand, of course, because you have to go to the Perron's diagram and move around the Perron's diagram, go to the future no infinity, past no infinity. And this is how Hawking did initially. But of course, there is also a path integral approach which obtained the same, but by exploring the fact that the poles of the propagator became periodic. And that's why but some people claim that Hawking was not rigorous enough. And that's what brings the information paradox also, because could bring, because there might be non-thermal modes also. There is a chance that this happens. This looks, of course, too simple, no? So it looks like a simplistic approach. There is a chance that there are some details that he simply omitted, and many people are working on that precisely, trying to find these non-thermal modes. Myself, recently we have a publication. I didn't show those results here. Accepting classical and quantum gravity with my good collaborator Abhishek Mehta from India, where we found some possible non-thermal modes. But of course, that part I didn't show this in this talk because I just wanted to show the essential, no?
I think it's still difficult to understand. For example, I'm the detector. I hold a ferrometer. Before you are the backhoe. Before you collapse in the backhoe, my thermometer is 0 temperature. But after you collapse, then I perceive some temperature from your Hawking radiation. But how do I know you form a backhoe or not? It's just Schwarzschild. When I far away from you, it's just Schwarzschild matrix. So the vacuum, same as before and after you collapse. That's like difficult.
Apparently the same, but
that is what you described.
Well, the quantum level is different.
Before and after you collapse, you say my vacuum changed. Maybe I'm not, but if you're Schwarzschild, I don't know your backhoe or not.
Well, classically it doesn't change, but because you are very far away now, you don't feel gravity anyway. But at the quantum level, if we take this approach serious, it's different. It changes, and that's why we can portray the black hole as a system permanently trying to find an equilibrium condition, unsuccessfully. So it's an unstable object. It's trying to reach the equilibrium but fail, and continue, and that's why the evaporation process happens. That's something I explain here, right? Because you can create a Lagrangian for reproducing the Hawking radiation. This is Lagrangian reproducing the Hawking radiation, actually. Ignore the kinetic terms, and you have the potential. This is particle number operator, quadratic, cubic, quartic. The difference with the standard case is that the standard case doesn't have the cubic term. Normally, people avoid the qubit term for symmetry reasons, for other reasons, etc. But for the thermal spectrum to appear, the qubit term is necessary. If you delete this one, it's just the standard K sigma model, etc. you see in particle physics. So when you minimize this, you have two possibilities: zero, but zero happens when m squared is larger than zero, and different from zero is when m squared is more than zero. So I can interpret this as a mechanism, this expression emerging as a mechanism of spontaneous symmetry breaking, where of course there are some broken generators associated, but the symmetry which is broken is the symmetry associated with the changes of internal configuration, which keeps the mass, charge, and angular momentum fixed in the black hole. And that's why I mentioned the no-hair theorem before, right? Then, of course, if in this case, the particle number operator will be an order parameter, because it will be zero before the formation, non-zero after the formation of the black hole. And that's why I could do this. I could assume all the possibilities equal zero, but then this will bring me a problem, because then some particle number operators will be negative. And how do you interpret them? Maybe antiparticles going out from the black hole, or what? So this interpretation is an issue also. But of course, the idea is that you can portray the Hawking radiation as a mechanism of spontaneous symmetry with this Lagrangian. Now, I can bet you that a generic theory, because if you use Einstein-Hilbert action, you will not obtain Hawking radiation, of course. You need to add something. A good theory of quantum gravity should be able, if want to reproduce a Hawking radiation, should expand to some limit a potential of this form, quadratic cubic quartic. Whatever it is, if you have an expansion in series, that it must have some resummation and goes to this limit somehow. What is the quantum theory? I don't know.
Okay, for this part, okay. So
yeah.
Remember, you said that the vacuum does not change here before the formation of the black hole and after. But now, if you use this formalism, it means the vacuum changed.
Classically, it doesn't change. At the quantum level, it changes. I mean, what we were discussing is that he said he perceived the same, but that's classically. At the quantum level, there are changes because the quantum fields will behave different. And that's the key point of Hawking radiation. Hawking put a quantum field over a classical background. Of course, we can debate, it's a semi-classical, maybe it's not accurate, but we are using quantum effects. So at the quantum level, the vacuum is changing. When the black hole is formed, that vacuum, quantum mechanically, is different now. It's different. So that's why you have to define other modes, and you can annihilate with those modes that vacuum. But when you compare with the old vacuum, the vacuum before, then of course is where you obtain the black hole evaporation process. Yeah, and that's why it's different. Yeah, if it's not for that mix of positive and negative frequencies, it will be the same. There are chances, of course, in our case. What happens if we have a mass which is not yet collapsed? Well, in that case, still the coefficient which mixes positive and negative frequencies will be this guy here. This coefficient in the Bogol-Wolff expansion. This guy will vanish. This guy here. Then if this vanishes, you have these two vacuums will be equivalent. I mean, the vacuums defined by these two modes will be the same. So the issue is a quantum issue. At the quantum level, they are different. And that's why, of course, we can model in this way. Of course, N is defined traditionally with the A daga A, as usual. And of course, I suspect that these things could be related to the information problem of black holes, which we are exploring. But of course, we use a different approach for analyzing the possible non-thermal modes, because of course, if there are non-thermal modes, there is a chance that there is information there somewhere. So we publish, I invite you to read this one, which is recently accepted, which not yet, I don't have yet the reference, but it was accepted a few days ago. So it's already online, but I don't know, they have not put the number. They just send the proof, we send it back, so it's okay. And of course, as you know, there are analog models of black holes. William Unruh himself, he analyzed. Okay, think in a moment. If you go to, think for a moment, you go to the Unruh effect, you can translate the other parameter to the acceleration, for example. The acceleration invariant could be taken as another parameter in such a case. No? 0 before, non-zero after. That's one issue. That's one issue which deserves to be explored. There are analog models. People do fluids, but it's not exactly the same, no, because William Unruh in British Columbia and these guys, they did some fluid experiments. They accelerated supersonic fluids, and you can create artificially an even horizon with some, because you send a sound back, it will never reach you because the fluid is supersonic. And they claim that some spectrum similar to Hawking appeared, but the paper was rejected always, I think. I mean, people didn't accept these results. So, well, still, you should know that these models exist. There are many others. And of course, in gravity, we have the Valley approaches. Yeah, the Valley and myself, I did following the Valley suggestions. Because, of course, the area of the event horizon measures the entropy, but in agreement with these guys, the entropy, the number of Nambu-Goldstone bosons, which should appear when the symmetry is spontaneously broken, should be proportional, should scale like the area of the event horizon. I assume it's because it's almost sure. It's because, of course, anyway, the event horizon, it contains information. It has to be in some discrete points, no? And each discrete point would correspond to probably to a Nambu-Goldstone. Well, this is not that solid. I think these ideas are not that solid. So that's why I don't explain so much here. Black holes can help us to model neural networks as sigmoids, because obviously if you see the Hawking spectrum is like a logistic function. It behaves like a logistic function. Like the sigmoid is the normalized version of the logistic function. So it's almost the same. So you can put information on quantum field in one neuron and then look how it maps. And when it maps it with different modes, there is a loss of information. These kind of things can be done, etc. One question is if de Sitter and de Sitter disperse in the same way the Nambu-Goldstone bosons. I didn't mention that because we didn't analyze deeply the behavior of the Nambu-Goldstone bosons, but remember that I mentioned that there are some issues of the dispersion relations depending on whether some symmetries are violated explicitly or not. So I give this open question: how to construct genetic theory of quantum gravity. So those are genetic theory of quantum gravity contains quadratic, cubic, and quartic terms generically, such as the ones I showed in this here, just now here in this potential. I would say yes, and I have seen that in other theories actually, not created with this purpose, but it's interesting that in some theories, battery low, but we are finishing. So what is the right theory of quantum gravity? The right theory of quantum gravity should reproduce the black hole evaporation also. It should reproduce it because it's a quantum effect. Other possible non-thermal modes, where this is why I promote this paper here. Then I made my conclusions. Hawking radiation for me is a manifestation of a mechanism of spontaneous symmetry weakening. The thing which thermalize the spectrum or delete the eraser of information is the qubit term. This qubit term is the guilty of the information to stay away. During the evaporation or process, the black hole tries to find the equilibrium condition. Remember, when the symmetry is spontaneously broken, normally if we go to the Mexican hat, where is the Mexican hat here? It will appear soon. When you are here in this one, or maybe the other is better, this one, normally this going down is not a mountain. Only when you change the parameters, it becomes a mountain, and then any perturbation forces you to. In the case of black holes, this process happens continuously. The black hole is in an unstable equilibrium, boom, jumps to, and then again repeats the process and repeat and repeat and repeat. And this is what generates the Hawking radiation, the black hole evaporation process. And yeah, those are my conclusions. And I think the time is over, so I overpass a little bit. Thank you very much for the chance to give this talk.
So, which symmetry break to make these Gaussian bosons, and what are the Gaussian bosons?
Well, yeah, it's true. I didn't show about the number of Gaussian bosons, but the symmetry I consider